So to find the F value, you don't use the Colebrook equation, I don't know, ever, but you do use the Moody diagram. So the Moody diagram is created based on the Colebrook equation. Just someone's done all the work in advance and put it into a diagram that we can actually use. In order to use the Moody diagram, we need two things using three different variables. We need the Reynolds number, as we said we would, based on D. We need epsilon, that surface roughness, and we need the diameter of the pipe. So the Moody diagram is designed for circular pipes, and we'll talk in a second about how to modify it to account for non-circular things. But this is what the Moody diagram looks like. So this is taken from a fluid mechanics book by Frank M. White, which we've used before for certain things. And this, here is what the Moody diagram actually looks like. So here it is here. Let's see, I'll try to focus the thing on that, see if it'll zoom in a little bit. Okay, and I'll zoom in. All right, not bad. Yeah. There we go. Now let's focus again. All right, so what you're looking at here, on the left-hand side, we've got the friction factor, F. So this is where your friction factor values are here. They range from 0.008 all the way up to like 0.1 up here. This in the bottom is your Reynolds number. So here's your Reynolds number along the bottom, ranging from about 1,000 way down here, all the way up to very large numbers, 10 million up here, 100 million up here. So these are the big range of Reynolds numbers along the bottom. And then these lines correspond to your various surface roughness, your E over D. So if you have an E over D of 0.1, you would follow this line. E over D of 0.002, you would follow this line. So you pick out what your E over D is, you follow the line over to your Reynolds number, and then you can look over here and pick off your F value. So that's how this works. This line here is 64 over the Reynolds number, so that's your laminar flow one. So your laminar flow friction factor is here, and then you see the transition to turbulence here occurring at around 2,000, the Reynolds number of 2,000, where it goes from laminar to turbulent. And notice that the friction factor jumps up for any surface roughness. If you have turbulence, you have higher friction than if you have laminar. As I said before, turbulence creates greater friction than laminar flow does because you're bringing that fast-moving fluid in direct contact with the wall. So we see if you can stay laminar, you can reduce your friction, but after you go to turbulence, the friction jumps up even if you have very, very smooth walls. And of course, it can get much higher if you have rough walls. So that's what the Moody diagram is going to do. You're going to use this diagram to get your friction factors by looking up your surface roughness, your Reynolds number, and then picking a thing off the chart to get your friction factor. Now, what if you have a wall that isn't a pipe that isn't circular? What do you do then? So for non-circular pipes or channels, circular pipes or channels, we can use the same relationships, but we replace D with the hydraulic diameter. And this is not an exact thing. Of course, if you just took a look at that Moody diagram and you paid attention, you'll realize, I got to zoom back out here. You'll realize that you're not going to be exact anyway. You're trying to pick a value off that silly graph. It's not going to be particularly accurate. So you're again back in the land of approximation here if you're using the Moody diagram. But anyway, hydraulic diameter. So hydraulic diameter is an approximation that allows you to use all of the same tools we just used for finding friction factors and for finding pressure drops. If you have a non-circular situation. So here is the definition of the hydraulic diameter. It's usually symbolized with D sub H. It's 4 times the cross-sectional area divided by the wetted perimeter. So if you want to look at a circle, just to show you an example, for a circle, we're going to say that DH is equal to 4 times the area, which is of course pi r squared. I'll put r naught there just so it's not confusing for us. And then divided by the perimeter, which is 2 pi r naught. And of course the r naught is going to cancel there. The pi is going to cancel. One of the r naughts is going to cancel. And I end up with 4r naught over 2, which is equal to 2r naught, which is equal to d. So the hydraulic diameter for a circular pipe is just the diameter, which makes us happy. But it's not always the same. It's not always just the diameter. Some things don't really have a diameter. But you can always use the hydraulic diameter in these relationships. So if you wanted to do a non-circular pipe, you use the hydraulic diameter to find the Reynolds number. So it would be a Reynolds number based on hydraulic diameter. And then you would use the hydraulic diameter to find your surface roughness as well. So your surface roughness thing, well, that's still looked up on the table, but you would divide it, instead of by D, you would divide it by DH. And if you use this DH for the Reynolds number and this DH for the surface roughness parameter, you can look up F on Moody diagram again. So you can still use the Moody diagram even for non-circular pipes. This is for non-circular. If you want to, and that's how people do it. So you find the hydraulic diameter, which we defined again. I'll write it here again for you. DH equals 4 times the area divided by the wetted perimeter. So that's the hydraulic diameter. That's a times symbol. 4 times the area divided by the wetted perimeter gives you the hydraulic diameter. You find the Reynolds number based on that. You find the surface roughness parameter, epsilon over DH based on that. You go back to the Moody diagram and you look it up.